All right, guys. So this is the review for exam 3 on exponential and logarithmic functions. And so hopefully you got a separate piece of paper and to practice these problems with me. So we're going to start with solving some equations and working with some properties of exponentials and logarithms. So here we have a bunch of exponential and logarithmic equations. We're going to start with A. And so remember, how do you solve an exponential equation? Or first, what is an exponential equation? You have x in the exponent. And so to solve this, it's actually kind of nice because you already have the exponentials separated. So you're just going to ln both sides. So we'll ln this side and we'll ln that side. And notice I always apply the ln's on the left. And what that'll do is that'll force those two exponents to come down in front. So we're going to get 4x ln of 3 equal to 2x minus 1 in parentheses, because that's all times ln of 5. And so we basically go from an exponential equation up here and then apply ln's, and we get a linear equation below. And then to solve this one, we have to unlock the x stuff and get it all over to one side. So we'll multiply through here by ln of 5. And so we have 4x ln of 3 equal to, and then 2x ln of 5 minus a 1 times ln of 5, which is ln of 5. And then we'll subtract this 2x ln of 5 off from both sides. So minus 2x ln of 5 on both sides. And we just add the columns together. And so what do we get? Well, we get this 4x ln of 3 minus a 2x ln of 5 on the left equal to, on the right, these are going to cancel, and we just have negative ln of 5. And then finally, to get x by itself, we realize we can just factor it out. So pull this x out, and then we have something minus something equal to negative ln of 5. And then what are the somethings? Well, what goes here times this is that. And of course, that's 4 ln of 3. And then what goes here times this is that right there. And of course, that's 2 ln of 5. And so now, since we're multiplying by this crazy thing, we can just divide it out on both sides. So we divide it out by 4 ln of 3 minus 2 ln of 5 on the left. And the same thing on the right. So 4 ln of 3 minus 2 ln of 5. And so we get x equal to negative ln of 5 divided by this 4 ln of 3 minus 2 ln of 5. That's our exact answer. And then if we want to check our work, we can check our work with the calculator, and it's not too bad. But we do have to make sure we put this in correctly. So how do we do that? So let's turn this on here. And we just type in, use the negative button. So negative ln of 5 in parentheses. And then divided by, now you're dividing by a difference down here in the denominator. So you need to make sure you put it in parentheses. So left parenthesis, 4 ln of 3 in parentheses on the ln minus 2 ln of 5. And in parentheses on the ln of 5, and then in parentheses for that denominator, and then hit enter, and it'll spit out our answer. And so to 2 decimal places, this would be negative 1.37. So approximately negative 1.37. So that's what it should be approximately to 2 decimal places. And then again, you can check your work by simply plugging it in over here into your last answer. I'm gonna get rid of this thing. All right, and so let's plug it in on this side. So basically you have 3 raised to the 4 times that answer. Oops, 3 raised to 4 times that answer. And so you can see what you get out on the left-hand side. You get that number out. And then we want to plug it into the right-hand side. So to do that, you can pull up the last entry. If you hit it twice, it gets to the second entry. So there's that number again. And hopefully we get 0.0024, blah, blah, blah when we plug it into here. So let's check it. 5 raised to the 2 times that answer, and then -1 up there in the exponent. And we see the answers are exactly the same. So check. I don't think it's right. I now know it is right. Okay, but that's the idea for that one. Okay, let's move on to the next one here. And so the next one, this one's a little probably too, I want to say, gimmicky maybe for an exam, but it's a nice problem for the review, because the idea of this one is you have an exponential function, an exponential equation, sorry, because you have x in the exponent, but it also incorporates a quadratic. So when I look at this thing, I'm like, oh, you're a quadratic kind of into disguise here. So notice this e to the 2x, that's actually, if you rewrite it, you can think of this as e to the x being squared. So you have basically something squared minus 8 times the something, and then plus 7 equal to 0. And so what we can do is we can kind of rewrite this in terms of give it another form maybe. So like instead of e to the x, let's just write, let's write u. So this is u squared minus 8 times u plus 7 equal to 0. And so what we can do is we can factor that quadratic on the side if you want. If you need this help, you can do that. So it's u plus or minus something, u plus or minus something equal to 0. And of course, the something comes from 7. There's only one way to factor 7, 1 and 7, because it's prime. And then they get that -8, it's a minus minus. And so we see if we let this e to the x here be our u, then we can factor it like that. So instead of writing u, we just replace it with e to the x. So if you factor this with e to the x, it's e to the x minus 1 times e to the x minus 7. And that's all equal to 0. And so remember, when you have this times that equal to 0, then we know it's a property of the real numbers that either this is 0 or that's 0. And so from this thing, we can say either e to the x minus 1 has to be equal to 0, or e to the x minus 7 has to be equal to 0. So from that one exponential equation, which is kind of like a little bit of a quadratic on the side, we factor it and we get two other exponential equations, not linear, but 2 other exponential equations, which we can solve. So we add 1 to both sides here, and we get e to the x equal to 1. And then remember, how do we solve an exponential equation? You get the exponential by itself, and then you can just ln both sides. So we ln both sides here. That brings down that exponent x. And so we get x ln of e equal to the ln of 1. And then you can check this on your calculator, but ln of 1 is 0. That's just going to go away. And ln of e is 1. So you just get x equal to 0. So there's one answer. And then the other answer comes from right here. We add 7 to both sides. And we get e to the x equal to 7. And now again, to bring down that exponent, we'll simply ln both sides. Those ln's always being applied to the left of the expression. And so x will come down times ln of e equal to ln of 7. And then remember that ln of e is always equal to 1. And so we just get x equal to ln of 7. And there's our second answer. And if you want, you can check these too. Make sure that we did them right. Okay, let's move on to some logarithmic equations now. So let's C and D, and we have both kind of types here. So the first one, we're just going to do what it says. So we have log base 3 of x minus 2 equal to 4. So what this says is basically 3 to the 4 is equal to x minus 2. And so let's write that down. So 3 to the 4 is equal to x minus 2. And then 3 to the 4, that's 3 times 3 is 9, times 3 is 27, times 3 is 81. So we get 81 equal to x minus 2. And this is a linear equation. So now we just add 2 to both sides and we get our answer. So 83 is equal to our x. And then part D, oh, let's check this one. All right, so let's check this one because sometimes it's hard to enter a log that's not base 10 or base E because you don't have that button necessarily on your calculator. It's not easy to find, right? So if I was going to check this log base 3 of x minus 2 equal to 4, what I probably would do is I would just rewrite this as ln of x minus 3 over ln of 3. And I'm sorry, that's not a 3, that's a 2 there. So ln of x minus 2 over ln of 3 is supposed to be equal to 4, or should be equal to 4. And so on my calculator, what I can do is I can check this by simply plugging it in here. So I'll do ln, and I found the answer to be 83. So 83 minus 2 in parentheses, and then divide by ln of 3. And if I get out 4, I know it's good. And if I don't, I know I made a silly mistake someplace, but I do get out 4, so I'm good to go. So now I'll put a little check mark here because I know it's right. I don't think it's right. I know it's right, so I just checked it. Let's do part D. So there's kind of 2 ways to solve logarithmic equations. 1, you do what the log says. 2, you can get logs on both sides and just drop them off because they're 1-to-1 functions, basically. Or if you like, the operation is 1-to-1. All right, so let's look at this one. And this one involves some properties of logarithms. So remember those properties. We'll use these in a little bit, but remember when you subtract logarithms, you divide on the inside. When you multiply a logarithm by a number, you can move it back up into the exponent there. So I can rewrite this if you want as what? Single logarithm ln of, and on top I'll have x plus 9. And then I'll divide by, because you're subtracting, and on the bottom I'll have x plus 3. And then that thing will be squared because you're multiplying it by 2. So those are those 2 properties of logarithms. I'm using the quotient rule and the power rule. And then on the other side, it's just equal to itself, it doesn't change, so ln of 1 over x. And so now that I have a log of this equal to log of that, remember the log function is 1-to-1, the operation is 1-to-1, so you can just drop it off. So I can drop off the ln's. I'll write here 1-to-1 implies that the inside pieces are exactly the same. So it's kind of a nice idea. Remember, 1-to-1 means like if you know what the output is, you know what input it came from. So this is saying right here, if you think about it, this is saying the 2 outputs here, ln of this is equal to ln of that. So if the outputs are the same and it's 1-to-1, we know the inputs have to be exactly the same too. So right here, I can write x plus 9 divided by x plus 3 quantity squared has to be equal to 1 over x. And so I go from a logarithmic equation down to a rational equation. And remember, to solve rational equations, we got to do that thing called clear the denominators. Very powerful little technique here, right? Clear the denominators. So we simply multiply by an x on both sides because there's an x here. And we also multiply by this x plus 3 quantity squared. So this whole thing is going to be put here. So we multiply that by that, and we multiply this side by that. And when we do that, what happens? Well, on the left-hand side, you're going to get an x plus 9, right? That stays in the top right here. But the x plus 3 squareds are going to cancel on that side. And so you're just left with this singular x, basically. So you get an x right here. And then it's equal to, on the right-hand side, the x's are going to cancel. That 1's going to stay. You don't really have to write it, but we will. But the x plus 3's squares stay too. So x plus 3 quantity squared will stay too. But again, the x's are going to cancel on that side. And so that's what we get. So we move from a rational equation down to a quadratic equation. Now it's time to multiply everything out. So we're going to multiply through by this. And so we're going to get an x squared plus 9x. So remember, to solve a quadratic equation, the idea is just get everything over to one side. And hopefully, right, fingers crossed, we can factor. And then this one's going to be an x squared plus, and don't forget there's a middle term here. So 3x and 3x is 6x plus 3 squared is 9. And then I'm going to subtract this x squared and 9x from both sides. So I'll do it on that side and on this side. So remember, if you perform an operation to one side, you just have to do it to the other. Doesn't matter if it's right or wrong, as long as you do it to both sides, still the equation remains valid. And so notice on this side, these just all cancel. And you get 0, which is exactly what I wanted. And on this side, the x squared cancel, which is nice because it means it really wasn't quadratic. It's really linear in disguise. And 6x minus 9x is negative 3x, and then plus 9. And so now we can solve this linear equation by moving over the 9. So minus 9 on both sides. We get negative 9 equal to negative 3x. And then finally, divide out by this negative 3 on both sides, and we'll get x. So negative 3. So negative divided by negative is positive, and 9 divided by 3 is 3. And so 3 is equal to my x. And again, you can check that answer to see if it's right if you want to. And if it's not, you probably made a silly mistake, but it's good. So. All right, so that's solving exponential and logarithmic equations. Then we come down here to doing some work with calculators and exponentials and logarithms. So if you have a calculator, right, take it out. And let's just work these problems together. I'm going to round these to 4 decimal places. So on here, I'm just going to type in e to the square root of 5. So second ln, and then put second square root and put a 5 there and hit enter. And out pops this number. And then the 4 decimal places, the 5th decimal place is 6. So we're going to round up. So that's 9.356 5. So that's approximately, if I can get my pen to work here. So approximately 9.35. I said what, 3565. So let's check that again. Make sure I didn't make any silly mistakes because it doesn't stay on the screen. So 9.3565. Yeah, because you have a 6 in the 5th decimal place, you round that up, and that's the answer. Let's do ln of 13. So ln of 13. Oops. So hit the ln button, then 13. And then in parentheses and enter. And it spits out 2.5649, and the 5th decimal place is a 4, so you just drop it off. So 2.5649. So 2.5469, and that's approximately. Oops, I think I transposed those numbers, didn't I? Let's check it. Looks like I might have. Yeah, 564. So let's fix that. So where's my eraser? There it is. So 64. So 2.5649. And then finally, this last one, which can be kind of tricky. So remember, there are a couple ways to do this on your calculator. The best way to do this is to rewrite this in terms of ln's. And so let's do that. And this will help you later with the algebra in calculus. So remember, this is the same thing as ln of 5 over ln of 2. And then we can put this into our calculator, and that'll tell us what the answer is. And maybe I'll say why that's true. I don't think I've ever told you guys why that change of base formula actually works, because it's not easy to see. So ln of 5 divided by ln of 2. And then hit enter, and it spits out this answer, 2.3219. So here, actually move this around. So 2.3219. Right, and then get my my answer here. Let me check that, make sure I didn't do anything bad. Yeah, that looks good. Right, so that change of base formula, what you have to remember is, what this number actually is. Right? Remember, it's an exponent. And it's the exponent that does what? It's what you raise 2 to get 5. And so over here, we're going to ask ourselves what this thing is. And so this should be the same thing. It's what you raise 2 to get 5. But if you think about these things, this is the exponent you raise e2 to get 2. This is the exponent you raise e2 to get 5. And so we want to basically say, this is the same thing. This is the exponent you raise 2 to get 5 also. So it's a little hard to see. That's why I usually don't show it to you in class. But notice, if you write it like this, right? it should be 5. And is it 5? Well, you have to do a little bit of work to show that, because you have to rewrite 2 in terms of an e, right? So remember, how do you rewrite 2 in terms of e? Well, 2 is the same thing as e to the ln of 2, because of that identity property, right? E to the ln of the anything is the anything. And so we can rewrite this as e to the ln of 2, and then raised to the ln of 5 over ln of 2. And notice what happens to the exponents here. They're going to multiply, and then they cancel. And so those ln of 2's cancel, and you just get this equal to e to the ln of 5. And then again, that identity property, remember what happens, the e's and ln's cancel, and that gives you the 5. So yeah, this and this are exactly the same, right? They're both the exponent you raise 2 to get 5. All right, so I don't think that's something you need to worry about, but it's kind of nice to see how it works. But the best thing is just remember, hey, it's ln of the top, right? That's the top basically, divided by ln of the bottom. And if you remember that, then you can always change bases when you need to. All right, let's move on to using some of these properties of exponents and logarithms to simplify things. So let's look at this first one here. We've done a couple of these now throughout the semester. So for this one, there's a number of ways to handle it. I like to take care of that negative first. So remember what a negative means: move the top to the bottom and the bottom to the top. So notice you have a top, which we call the numerator, and we have a bottom, which we call the denominator. And you just flip-flop them, right? We just basically write the reciprocal of that. That's what that negative actually means. And so that's x to the 6 on top, and y to the negative 5th on top, and then divided by a 2x on the bottom. And that's all still being cubed. Now, what I can do is I can just cube everything. So when I say cube everything, I'm going to cube this, I'm going to cube this, I'm going to cube this, and I'm going to cube that. So this will be equal to x to the 6 cubed, exponents multiply, so I get x to the 18. Y to the negative 5th cube, again, exponents multiply, so I get y to the negative 15th, divided by 2 cubed is 8, and then x cubed. And then I just cancel off what they have in common. So here, these 3 will cancel off with 3 of those and leave me with 15. And so I'll get x to the 15 on top, divided by 8 on the bottom. And then because that's a negative exponent, I'm going to move this thing downstairs. So over y to the 15. And that's my answer. All right. So let's check it. I'm going to try to make any silly mistakes. Yep, that looks good. And then, so that's property, working with properties of exponents. And then we come down here, I'm going to do some properties of logarithms now. And so what is this actually equal to? And so remember, we have those 2 identity properties. And so over here, maybe we can practice writing those down. So, all right, we can write right here if you want. So identity properties. There's 2 of them. We'll write both of them down, even though I'm just going to use one of them here. So what's the idea? The idea is you start with x, you take b to the, and then do log base b of it, and undoes it and gives you back x. And there's also a second one where instead of, you start with x again, but instead of taking b to the, we do the log first. So log base b of it, and then do b to the, and then I'll give you back the x. Right? They're called the identity properties because you start with x and you wind up ending with x. So this one, if you think about it, it looks mostly like this. And so it's log base b, and the wish notice is b to the anything. So 1 over 27, remember, can actually be rewritten as 1 over 3 cubed, which is equal to 3 to the negative 3. So this is actually log base b, so that's a 3, of 3 to the negative 3. And so log base b of b to the anything is the anything. So it must be equal to negative 3. And in fact, we can kind of think, if you want, it's kind of like the log base 3 cancels with the 3 to the, because they're inverses of each other. And so it just spits back, or gives us back, this negative 3 right here. Let's look at this one, which I didn't leave much room for. So let me let me just move that up here. So for C, I have e to the 3 ln of 2 minus ln of 5. Move that up a little bit. And this one is going to use some properties of logarithms, of course. And so let's write these down. So these are the log laws. I'm going to put them down here because we're going to use them. These are their problems down here. So the log laws. And so remember the log laws, there's 3 of them. So 1, 2, and 3. There's what's called a product rule. And the product rule basically says if you have log base b of m and you add log base b of n, it's going to be equal to log base b of m times n. And there's also what's called a quotient rule. And that one says if you have log base b of m minus log base b of n, so basically you're subtracting exponents in a sense, you're going to get back log base b of m divided by m, which is basically saying you're going to get back the exponent of when you divide the exponentials, right? So when you divide exponentials, you subtract exponents. That's what that's saying. Whereas the one above it is saying when you multiply exponentials, you add exponents. Let me get rid of those lines. And then the last one, the last log law is a power rule, which basically says if you have log base b of m to a power, that power that's in the exponent there can come down in front. So it's p times log base b of m. All right, so let's come back up here and look at this and notice, here you have times 3, and you also have a minus. So what we can do is use this rule 2 and this rule 3 and combine these logarithms. But we're going to do it one step at a time. So this will be equal to e to the, and we'll use rule 3 first, right? So by rule 3, that power rule, that exponent can go back up here. So we get ln of 2 cubed, and then minus ln of 5. And then that's equal to, we'll take care of this minus, so that's ln of, and 2 cubed is 8, so 8, oops, my bad guys, hold on, let's fix this. Change colors too soon here. So equal to, that e stays there, guys, that's important. So e to the, now let's change color. So by that quotient rule, because we're subtracting, that's going to be ln of, and 2 cubed is 8, so that's 8, divided by 5. And then finally, by this property here, b to the log base b of the anything is the anything. So notice you have e to the ln of the anything is the anything. So 8 over 5. In some sense, it's like the e's and ln's cancel each other out because they're inverses of each other, right? It's not like they really cancel. They really undo each other. It's probably a better way to say it, but cancel, I think it's okay. And so that's 8/5, especially when you're just learning. Okay. Now we move on to number 4, condensing and expanding logarithmic expressions. So this is a good one. And so let's practice some of these. So notice in this one here, you have division, you have multiplication, and you have several exponents, you have to the 5th power, and also square root of z right there. So you're going to use all 3 rules at some point in time. Of course, which rule to use first is the one that applies to everything. So we're going to use the quotient rule first, because that applies to this top and bottom. And so that'll be equal to the log of the top, so the log of x times y to the 5th, in parentheses, and then minus the log of square root of z, which I'm going to write as z to the 1/2, because I know that square root is really a power. It's really an exponent. It can be written as a power. So I'm going to use that power rule eventually on it. But before I use the power rule on this, because that y to the 5th is kind of attached to that x, I'm going to use that product rule to separate it. So the product rule basically says log of this times that is going to be the log of this plus the log of that. And then we still have this minus log of z to the 1/2. And then finally, we can come over here and use that power rule to bring these exponents down in front. So remember, one step at a time, nice and slow, showing all our work. So log of x plus 5 log of y minus 1/2 log of z. And there's our answer. That was expanding logarithmic expressions. Now we're going to practice condensing or contracting, however you want to say it. So we're going to rewrite this as a single log base b. And again, you can see we're definitely going to use that product rule there, or the power rule right there, because you have a 2 and a 5. You're also going to use that quotient rule because you have a minus there. You're definitely going to use that product rule because you have a plus there. And so which rule are you going to use first? Well, you're kind of forced to use that power rule first because you have to get rid of those 2s and 5s. Notice there's only 1s on the product and quotient rule. So to get rid of that 2 and 5, we can rewrite this by the power rule and simply put those powers back up into the exponents. So it's log base b of x squared minus log base b of y to the 5th, and then just plus, this doesn't change, it's just log base b of z. Then I have a minus and a plus. And so on this one, we have to be a little bit careful because remember I said sometimes the order matters and sometimes it doesn't. It just kind of, depends. So to be safe, always work left to right, because if you try to work right to left on this one, you're going to make a mistake. So we start with the subtraction then. And so we turn this into division. We use that quotient rule. We write this as the log base b of, and you have x squared on top and y to the 5th on the bottom. And then plus this log base b of z. And then because you're adding here, we can use that product rule now to bring these together. So we get log base b of x squared over y to the 5th times a z. And then remember, when you multiply by z, it's like multiplying by z over 1. So the z goes on top and the bottom stays the same. So it's really just log base b of x squared z divided by y to the 5th. And that's our answer. Again, one step at a time, and then be careful. Always work left to right when when you're not sure which one, subtraction or addition, to do first. And that is an order of operation type of thing. You have to be a little bit careful there. So always left to right. All right, I'm going to check this, and it looks good. All right, so I think that's it. That's all we had on that for that part of the review. I don't see any more. All right, let's look. That was the last one, I guess. Okay, so A, B, just A and B on that one. So let's now look at the next part. So this review split up into, I think, 3 parts, right? So the first part, just to kind of look at the big picture, the first part are just working with these equations, so solving exponential and logarithmic equations, and then working with the properties, right? So exponential and logarithmic properties. And then the next part we break into is the function part. So this is, sort of finding the formulas, finding the graphs, finding the domain type problems, graphing, logarithmic, X-intercepts, Y-intercepts, asymptotes. And then we get into the modeling problems, which are more like the word problems in this section. So, using exponential functions to solve problems, finding exponential functions, using logarithmic functions to solve problems, and so on. So let's come back up to the function section and start, doing number 5, which number 5 is a great problem. It's super tough. It doesn't get any worse or any harder or any better, however you want to look at it, than this one. So if I can, I like to start with a picture on this one. And so I want to find the formula for the exponential function with f of -1 equal to 3 and f of 3/2 equal to 96. So let's just kind of get in here, x and y. And f of -1 is equal to 3. So I'm going to put -1 comma 3 there. And f of 3/2 is equal to 96. So if you plug in 3 over 2, you get out 96. And so basically, I want to find the formula for that exponential function. And notice I missed that point there, which is like, that's okay, just erase it and then put it back on there. But you can see it's decreasing, you know, and since it does say graph it at the end here, we'll graph it. So remember there's a there's a horizontal asymptote at y equals 0. So we'll put that on there. And there is a y-intercept, but I'm not sure where the y-intercept is. So I need to go find that still. All right, so I want to find, right? I want to find the formula for the exponential function. So exp of cn. So my equation, that's given to me on the front of the, it'll be given to you on the front of the exam. So I know what it looks like. It looks like this. I have f of x equal to, and it's c times a to the x. In fact, if you look at the front of the review, you'll see the formula at the top. So my job is to find this c and a. And to do that, I'm going to use this information that they give me. So they tell me if you plug in -1, you get out 3. And so if I have c times a to the -1, I get out 3. And then this point says if you plug in 3 halves, you get out 96. So c times a to the 3 halves is equal to 96. And so the important part here is to make sure you understand how the graph and the formula are connected to each other, right? Points on the graph come from the formula, basically. And so over here, we're going to start on the left, because that's what I like to do, but you can start on the right if you want to. But this one's kind of tricky to solve because of that negative exponent. So remember, what a negative means is put it in the denominator. So that means do c divided by a is equal to 3. And as soon as you write this, typically you guys are kind of good to go. So let's move the a over. So we'll just multiply both sides by a, and we get c equal to 3 times a. Right? So when you multiply it through here, the a's cancel on the left and you get 3 on the right. And then the idea is take this 3a and plug it in for the c right there. And so this will be 3 times a, and what color coordinate this, times a to the 3 halves is equal to 96. And so now it's kind of like one of those problems where you're working with exponential properties of exponents. And so notice here, exponents are going to add, and so it's going to be 3 times, and then 1 plus 3 halves. Let's just do that over here. So 1 plus 3 halves. Well, remember, you're going to find a common denominator here. So it's just multiply top and bottom by 2. And so you get 2 plus 3, which is 5 on top, and a 2 on the bottom. So that's a to the 5 halves is equal to 96. And so then we'll divide both sides out by 3. And so when we do that, the 3's will cancel, and we'll get a to the 5 halves is equal to 96 divided by 3 is a 32, I believe, right? Yes, 32. And then how do you get rid of the 5 halves? So this is the tricky part, okay? There are a couple of ways to do this. I think the easiest way is just probably to raise both sides to the 2/5. That's probably how I would do it. So to get rid of 5 halves, I'd raise this side to the 2/5 and raise this side to the 2/5. And so when you multiply exponents here, notice the 5's cancel and 2's cancel, so you just get back a. And then 32 to the 2/5, you can check this on your calculator. I don't have any issues with that. So if you want to use your calculator to interpret that, you can. Although you can do this by hand. So let me just show you in your calculator how you do it. But you take 2 and you raise to the 2/5, and it tells you that's equal to 4. Well, of course it's equal to 4, because remember what this number means. This means take the 5th root. So that really means take the 5th root of 32. And then this number here means to square it. And so if you can do this by hand, it should be a pretty nice number. So the 5th root of 32, it's not 3. 3 is too big. It's got to be 2, right? So 2 times 2 times 2 times 2 times 2, you'll see is 32. So it's actually just 2. And then you want to square it. And so, of course, you get 4 back. And I don't mind if you use your calculator in the end there to compute that number. I think that's okay. Knowing that you raise it to the 2/5 is awesome on both sides. Okay, so a is equal to 4, but now be careful. We did a lot of work. Are we done? No, because we still need to find the formula for the exponential function. That means you found a, we still need to find c. So c is equal to here 3 times a, so 3 times 4, which equals 12. And then finally, so there's our c, we have to come back here. So therefore, our function f of x is equal to 12 times 4 to the x. So it actually is not too bad a looking of exponential function, but it's a pretty tough problem to solve. Okay, let's go down to number 6. So number 6, we're going to find the domain of these new types of functions, the exponential function and logarithmic functions. Part A is kind of a trick question, but I mean, it's not meant to be a trick question, but the domain of exponential functions are everything. So remember, there's only 3 things that are going to limit our domain. So let me write that over here. So for the domain, what limits our domain? 1, remember, you can't divide by 0. And notice over here, there's no denominator. And then 2, if you have a square root, it has to be bigger than or equal to 0 on the inside. And it's really any even root. And the reason for that is you want to keep it real. If you get a negative number underneath a radical, and that radical is a square root or a 4th root or a 6th root, then it's an imaginary number. So we got to make sure it's bigger than or equal to 0 underneath there. And then finally, the third thing, this is the new thing in this section, is if you're working with a logarithmic function, you got to make sure it's bigger than 0 on the inside. Otherwise, you're in trouble, right? Why are we in trouble? Well, remember, logarithms you can only take the logs of positive things. And that has to do with the way that they're defined. Remember, they're defined in some sense just to be the inverse of an exponential. And the outputs of an exponential are always positive. So that means the inputs of a logarithm are always positive. And so there's no log here. So this domain is everything. So don't be tricked by the simple question of what's the domain of an exponential function. In this case, it's everything, right? Now, for part B, though, there's a twist. So for part B, this is a logarithm. So you have to worry about this inside piece. So you kind of go through each of these pieces. Is there a denominator? You say yes. And if you want to, you can take care of this. But since it's on the inside, it actually doesn't matter. So I'm not going to do it. There's no square root. But yeah, there's a logarithm. There's an inside piece. So we want to make sure this inside is always bigger than 0. So x minus 1 over x squared minus 9 is always bigger than 0. And like I said, if there's a denominator inside, 3 will always capture this. If it's on the outside, yeah, I mean, you have to worry about it. But on the inside, it's always going to be captured by that third requirement for your domain. All right, so now, how do we solve this rational inequality? Well, like we solve all rational inequalities, we simply make a Sine diagram. And then in some sense, this is actually how you solve all inequalities besides linear. So you'll notice in this section, we didn't do exponential inequalities or logarithmic inequalities. And it's not that we don't have to do them. I guess those who have created pre-calculus some 50, 60 odd years ago decided that that was not something we needed to do since we did it with linear, quadratic, and rational. I guess they feel like you now have enough experience to reflect upon, to abstract into other types of functions. So let's not do that, I guess, is what they decided. But you will do it in calculus. So what's the idea of a Sine diagram? Well, you just make a number line, which is really the x-axis. And then we're going to find those sort of points where you have zeros or undefined. And then we can test points in between, or to the left or to the right. So let's find the zeros for this rational function here. Remember, that's just when the numerator equals 0. So you have x minus 1 equal to 0. And so you add 1 to both sides, you get x equal 1. And so right here, we'll put a 1, and that's a 0. And then we want to find where it's undefined. And so where is it undefined? Well, that's when the denominator is equal to 0. So x squared minus 9 is equal to 0. And so this is kind of a simple one. You can move over the 9, but I like to factor so I don't lose any information basically. Because sometimes if I don't factor, I'll forget that plus or minus on the square root. So I like just to factor. So x minus 3 times x plus 3 equals 0. Notice in this one, the middle term does go away because it's minus 3x plus 3x. And so that tells me either this is 0, so x minus 3 is equal to 0, or that's equal to 0, because you're multiplying them together. Right? Remember, you're multiplying them together to get 0. So one of those two has to be 0. And so this tells me x equals 3 when I add 3 to both sides. Or I have x equals -3. You subtract 3 from both sides. So over here, I'll put -3. Here, I'll put +3. And that's where your undefined. So usually I just UND or undefined. So what I've done basically is found the possible places where this function here, this function, not the ln function, but this function there, the rational function, can change sign. Right? So remember, if you have a function, most of them are basically continuous for the most part. There's just certain points that they may not be continuous. So for rationals, it's where they're undefined. And then you know the zeros. So now we know, like, if we test a point to the left or in between to the right, if it's positive or negative. So here we'll choose this point like -4. We'll choose 0 because that's a nice point between -3 and 1. We'll choose 2. It's a nice point between 1 and 3, and then 4 because it's a nice point to the right of 3. And we'll plug this in to this rational function here. So x minus 1 over x squared minus 9. And just see what happens. And again, I guess I'd like the factored form. It's just easier to plug into. So I'll write x minus 3 times x plus 9, plus 3, sorry. Actually, it's not that much harder to plug in x squared minus 9. But let's just do it. So -4, what do we get? We get -5 on top, divided by -4 minus 3 is -7. And then, oops, sorry. Kind of getting that -4 there. Yeah, -7, right? So -4 is -4 minus 3 is -7. And then -4 plus 3 is -1. And so you have a negative on top and a positive on the bottom is a negative times a negative is a positive. And so that's a negative. And so now I know if you plug in a number to the left of -3 into this thing right here, it's always going to be negative. Now let's plug in 0. So 0 minus 1 is -1. Divided by, I have -3 times 3 on the bottom. So negative by negative is a positive. And finally, let's plug in 2. Plug in 2. That's 1 divided by 2 minus 3 is a -1. 2 plus 3 is 5. And so that's negative. And we have one more left to do. So plug in 4 and I get 3 divided by, and on bottom, 4 minus 3 is 1 and 4 plus 3 is 7. And so it's positive. Notice the signs did alternate, but it only did that because, like I tell you guys, the problems are kind of they're the easy ones to set up, basically, right? The algebra is going to be really nice. And so now, what the heck do I want? I want when this is bigger than 0. So that's positive stuff. So I want all this stuff, and always parentheses on these because it's bigger than 0. And then I want this stuff to the right of 3. So therefore, my domain D of this function now, of ln of that rational function, is what? It's -3 to 1, union, so that's all this stuff here, union all this stuff over here. So union, parentheses, 3 to infinity. And if you want to, you could graph this thing up here and kind of check your work. So if I had time on an exam, I might go back and try to check my work by graphing it. All right, I'm gonna check my work here with the answers, and that looks good. All right, so that's part B, find domain of exponential functions, which domains out everything. And then logarithmic functions, a little trickier. You got some work to do, usually solving some sort of inequality. Let's move on to number 7, which is graphing. Oh, I just remembered, I forgot one way up here. So let me go back here. I still thought of graphing. I forgot to write down the Y-intercept here, guys. So what's the Y-intercept? It's the initial value. So this should be a 12 right here. So if you've already done that, good. If not, go back, put the 12 on the graph. Now it's good to go. We have the formula right here, and we have the graph right there. So now going back down to number 7, what do we have? We want to graph a logarithmic function. And so how do we graph logarithms? Well, we find the intercepts, asymptotes, put those on the graph, and then we can graph it. So over here, let's just draw a little graph. So I have x and y. And I want to graph this log base 2 of x plus 3 minus 5. Now, for fun, let's just get this going on our calculator just so we have an idea of what's happening. So I'm going to clear this out, hit y equals. Now it's kind of hard to graph this on your calculator. So to graph it on your calculator, you can do ln of x plus 3 divided by ln of 2. But if you have a newer calculator, you can actually just use these buttons, hit the math button, and go down to log base, and it'll give it to you right there. So you just put a 2 right there and kick it over, and then type x plus 3. And then kick it over, and then minus 5. And so then do zoom. We'll do a standard window because, we really don't know where to look. So we're hoping whoever wrote the problem set it up so it's like, oh yeah. And so we can see it over there. You see the y-intercept. You can't really see the x-intercept, but it happens out over there. So remember, it keeps going up just really slow. You kind of see it has a vertical asymptote on the left somewhere. And so now we're going to go find all that stuff. So how do we find x-intercepts? So let's do x-intercepts first. So here, x-intercept. And so remember, x-intercepts, we know it kind of happens somewhere out here. And what we know, we don't know how far it goes over, but we know we went up 0 basically. And so the idea is take this output and set it equal to 0. So let's do that. You take log base 2 of x plus 3 minus 5, and we're going to set it equal to 0. And so what we're left with is solving a logarithmic equation. So to solve this equation, we'll try to get the log base 2 by itself. So we'll add 5 to both sides. That'll give us log base 2 of x plus 3 equal to 5. And then we just do what the log says. So what does the log say? It says basically 2 to this is equal to that. So right here, I'll write 2 to the 5th is equal to log base 2. Oops, sorry. Right, we're doing what it says. The log goes away, right? So 2 to the 5th is equal to x plus 3. And it goes from a logarithmic equation now into a linear equation. And 2 to the 5th, what is that? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 32 is equal to x plus 3. And then take away 3 from both sides. And we get 29 is equal to x. So it's way out there. We'll just label it here, 29. Okay. And again, we're not drawing to scale, so don't draw to scale, otherwise you'll put yourself in a tough spot, basically. So that's the x-intercept. We still need to find the y-intercept. And so right here, I'll write, let's write the y-intercept. And so for the y-intercept, how do we do it? Well, that was equal to 0, so let's probably plug in 0. So it's just f of 0. And so what's that equal to? So that's log. So show your work, that way if you make a mistake, you can get full credit. So log base 2 of 3, 0 plus 3 minus 5, which equals log base 2 of 3 minus 5. And so that's y equals. So that's our y-intercept. So I'll put that down here. So I'll write this as log base 2 of 3 minus 5. So I found my x-intercept. I found my y-intercept. Now I need to find my vertical asymptote, so my VA. And so remember, how do you find the vertical asymptote of a logarithmic function? Well, you just look at the inside. Right? Remember, the inside piece always has to be positive. And so when it's equal to 0, something basically blows up, like something bad happens. And so that's where you get that vertical asymptote. So x plus 3 equal to 0. That's when the inside equals 0. And we subtract 3 from both sides and get x equal to negative 3. So there's my vertical asymptote. So we'll draw that on here. So dashed line. I'll write this one at the top. I think x equals negative 3. And then horizontal asymptote. So HA, there's always none. So we write none. There are none. So no horizontal asymptote on this one. If you want the little bonus point, you can say why. It's because as you take the limit, as x goes to infinity, of log base 2 of x plus 3 minus 5, it's equal to infinity. So remember, logs just get bigger and bigger as you go out to the right, but it goes really, really slow. Okay, so now I'm ready to graph the function, including the intercepts and asymptotes, which are already on there. And I have my calculator to kind of, just use it as a sort of guide and shape and form, right? So it's like, oh, it goes up, it goes up. Okay. So I think it's going to start down here. It's going to go up and out like that. And notice I kind of missed that little red point there, so that's okay. So I'll just tend to take my eraser on this little thing here, and erase it. And then I'll kind of redraw stuff here and I'll move it up. And that's okay. So you just move it up right on there. And so now it looks good. All right, so there's the graph of our logarithmic function. Intercepts and asymptotes and everything. All right, so now moving on to the modeling section. So for the modeling section, we have a bunch of word problems involving, exponentials and logarithms. So let's just kind of like head into it, right? So this one says the function s of x equal to 15 times 0.975 to the x models the percentage of surface sunlight s that reaches a depth x feet below the surface of the ocean. At what depth is there only 10% of the surface sunlight? Okay, so what are we trying to find? We're trying to find this depth. And so we have to decide, what is 10%? Is it X stuff or S stuff? And so if you look at this, it's actually not too bad, because you kind of see here, like, models the percentage of surface sunlight S. So S is definitely a percent that reaches a depth of X, but X isn't a percent, it's feet. So this is S stuff. So what we're gonna do is we're gonna take 10 and plug it in to our formula here. So 10 plugs in for S, and you have 15 times 0.975 to the X. So it's really just an output question. You plug in for the output and you solve the equation. In this case, it's an exponential equation. And so remember, how do you solve an exponential equation? Well, you got to get the exponential piece here by itself. So the first thing we'll do is just divide out by 15 on both sides. And so 10 over 5 is actually 2/3. 5 goes into 10 2 times and 15 3. So it's 2 times 5, 3 times 5. And that's equal to then a 0.975 to the x on the right side. And now I can simply ln both sides, and I'll bring that exponent down in front. And so I get ln of 2 over 3, maybe I'll put that in parentheses so to collect it together, is equal to x ln of 0.975. And then to get the x by itself, I'll simply divide out on both sides by this crazy ln of 0.975. Make sure you do it to both sides. So divide ln 0.975. Notice on the right, they'll cancel, and then we'll get our x by itself. So x is going to equal, and you need to write down the exact answer. So the exact answer would be ln of 2 over 3 divided by ln of 0.975. And then you can approximate next to it. So, how many feet would that be? So I definitely need a calculator to crunch that. So if you have a calculator, let's crunch this together. So on, and then let's clear that out. And then ln of 2 divided by 3 in parentheses, and then divided by ln of 0.975 in parentheses, enter. And so I get out about, let's say, just 16 years. So 16, not years, I'm sorry, feet, right? So remember, x is in feet, so 16 feet, just use the right years. All right, so about 16 feet, about 10% of the surface sunlight reaches it. And you kind of know this, right? So it's like, sun comes down the ocean, and if you're at the top, you can kind of see the light, but as you go down, it gets darker. The light doesn't penetrate as well. Okay, so that was kind of just an exponential function and doing an output question. Let's look at the next one. Number 9. And so on number 9, what do we have? Another exponential problem. And I know it's exponential. Why? Because of this percentage right here. So that percentage, I just look at it, I'm like, oh, that's an exponential question. So in this one's a little bit more involved. So let's make a picture out of it because it don't give us the formula. And so it says in 1980, so I'll write 1980, a certain city had a population of 2,000 people. So in 1980, you have a bunch of people here. It's my population. So just write a couple, right? 2,000 people. the population has grown at a steady rate of 3.5%. So it's increasing 3.5% each year. Find a formula that models, the size of the population, and then use it to determine the year it will reach 10,000 people. So what do I want to find? I want to find a formula for the population, and then, find the year then it reaches 10,000 people. And so you have two things you need to do. So let's find an equation first. All right, so for the equation, I know it's exponential, so I write down the formula for an exponential function. So f of x equals c times a to the x. And then I know what c is. C is this initial value, 2,000, so c is equal to 2,000. And I even know what a is. A is equal to, since it's growing by that percentage, which is 0.035, I just take 1 and add it to it. The 1 is the whole part, and the 0.035 is the additional 3.5%, so it's 1.035. And so the formula is just f of x equal 2,000 times 1.035 to the x. Or if you like, we can write this as p of t, which is equal to then 2,000 times 1.035 to the t. That's kind of how I'd like to do it. But if you leave it as f of x, there's no problem. I have no problem with that. And so there's the formula for the population. It depends upon the time. And so basically we got part 1 there. And then to do part 2, we have to find the year it reaches 10,000 people. So 10,000 people, that's not an input, that's an output. So we're plugging it in right there. So basically we have 10,000 equal to 2,000 times 1.035 to the t. And now we want to solve this exponential equation. So we're going to divide out both sides by 2,000 and get 5 on the left. And on the right, when you divide out by 2,000, it cancels. You get 1.035 to the t. And then we can just ln both sides. So we pull out our old ln, and that'll bring that exponent down in front. And so we get ln of 5 equal to t ln of 1.035. Let's make that 0 better there. And then we can divide out both sides. To get t by itself, we'll divide out by ln of 1.035. So it'll cancel on the right, and we'll have t equal to, the exact answer would be ln of 5 divided by ln of 1.035. And we can approximate that with our calculator. And so we'll turn this on, clear that out, and type ln of 5 in parentheses, and then divided by ln of 1.035 in parentheses. And then hit enter, and this tells us basically the number of years it's going to take for the population to reach 10,000 people, which is about 46.8 years. So let's write 46.8, and then don't forget the units, years. All right, so that one's kind of like the one we did before. So I don't know if I really needed 2 of those problems on this review. I didn't realize those were such similar problems. But yeah, let me just check my work here, guys. Right. So, and it said in what year, determine the year, right? So if you want, we could add that to 1980, right? If you add that to 1980, you get in 2026. That's not that big of a deal to me, but it does say in what year would that determine the year it would happen. Okay, so either of those answers are fine, fine with me. Okay, so looking back, all right. So I think, you know, 9 is much better problem than 8, I think. Right. So 9 is more involved. You have to find the formula, and then you have to do something with the formula. Right. So in fact, I should have labeled this. Now I'm solving here. And then the testing part is, you know, does it seem to be true? You know, does that work for you? And I guess, yeah, I mean, it makes sense to me. If it was negative, I'd say there's something wrong. If it was too far out in the future or too soon in the future, it might be wrong. Like I said, in 1 year, I'd say that'd be kind of strange. 2,000 growing to 10,000 in 1 year when you have 3.5% growth. That doesn't seem right. So testing is just kind of, does it make sense or not? Okay, let's move on to the logarithm type problems. And so on number 10, what do we have? So this one's nice. So on this one, they give us the formula. So that's when I say, like, whenever I see this, like, I see a formula in a word problem, like, it's going to be nice. It's not going to be too bad. So the percentage of cell phones with a camera can be modeled by this formula. So let's just copy it down. P of x equal to 8 plus 36 ln of x, where x is the number of years. Right, so that's what x is. After 2002, we want to predict the year that 90% of all cell phones will have cameras. So it's kind of an old formula because I think all cell phones now have cameras. But this was in 2002, so you guys may not remember 2002, but I do. And in 2002 is about the time everybody started to get cell phones. 2001, really, right? Before 2001, you had to be relatively wealthy to have a cell phone. But 2001 was basically the year that cell phones hit basically everybody. Right? Anybody could afford a cell phone. I think it was basically like cheaper than today. It was like 25, 30 bucks a month, and the cell phone was free. So it was almost as cheap as having a landline in your house, like a hard line in your house, you know, a phone in your house. All right, so, but what does a 90% mean, right? So is a 90% input or output? So you have to ask that question. And so X is years, and so 90% is not years. It must be output. So you plug in for here. So we type in 90 here, equal to 8 plus 36 ln of X. Now, look at this real fast. I did not convert that to a decimal. Why did I not convert that to a decimal? Well, look at the formula. It's 8 plus, not 0.08, but 8. So it's not converting percents to decimals in this problem. So you have to kind of look at the formula and get a feel for it and realize, yeah, I just leave the percent as is. All right, so now how do you solve this logarithmic equation? We're going to subtract 8 from both sides. And we're going to get what? This is 82 equal to 36 ln of, 36. We go here. Uh-oh. Hold on one sec, guys. This is not behaving for a second here. So let me get back down here. Cross my fingers. It's getting angry at me. Okay, let's go back here. And let's write 36 ln of x. Cross your fingers. Hope it doesn't crash on me. All right. And so now what do? We want to get the ln of x basically by itself. You know, that's our job. It's like get the exponential, get the ln stuff by itself, whatever, and then you can solve for it. All right, so let's divide out then. Since you're multiplying by 36, we'll divide out by 36 on both sides. It does reduce a little bit because these are both even. So, you know, 82 is what, 41? And then 36 is 18. So that's nice. You can reduce a little bit there, and that's equal to ln of x. And then this is often where we get stuck, right? And why do we get stuck here? We get stuck because we have to do what the log says. So remember, there's a little e down here we don't usually write. What the log says is e to this is equal to that. So e to the 41 over 18, that's in the exponent, is equal to that x. And as soon as you do that, you're basically done. I mean, that's the answer. We got to put the units on it. Now we will approximate it. So on my calculator, I'll approximate this. So I'll do second ln to get e to the up there and do 41 over 18. And it's nice to approximate because you want to make sure the answer makes sense. And what pops out is about 9.75 years, or let's just do 9.8 years. So about 9.8 years, which I think they're pretty much spot on. You know, I'd say definitely by 2012, probably most of the cell phones were approaching cameras. And then, you know, by now, all of them have cameras. I don't know if it's even an option to not have a camera. And we can do the year too, right? So if you want, we can add 2002 because that's where we started. Right? So we started here in 2002. And if you add that to it, what do you get? You get 2011, maybe, right? 2011. So in 2011. So that's also a good answer for this problem. Right, just remember on the word problems, don't forget the units. That's probably the biggest mistake. And it's not a lot of points, but I hate having to take off for forgetting units because I feel like you guys did such a good job solving the problem. All right, one last problem and we'll be done with this review. So this last problem involves using this exponential functions with E. And so this is a great one for just input and output. So here's the formula. So the formula P of T equal to 21.2 times E to the 0.0407 T models the population of a US state P in millions T years after 2000. Find the population in 2015. So first, just figure out your T value. If you start in 2000, 2015 means T is equal to 15. And so this is a pretty straight up problem. What's P of 15? And then just remember to show your work in case you make some silly mistakes. So 21.2 times E to the 0.0407, and then times 15, because T is 15. And then just use your calculator and we'll approximate the population. And so on this one, what do I have? So let me move this over so I can see it. And so I have 21.2, so 21.2. And then I'll hit second ln to get the E to the, and then 0.0407. And then I'll put a times 15 up there and hit enter. And it says about 39.03, blah, 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 people. So be careful here. I'm going to round this just to the nearest whole number. So this would be at 39, but you can't write people. You gotta write million people, because remember it's in millions. So there's the population. So in 15 years, the population, which actually even know what it started at, remember, so it's actually started at 21.2 million, is going to grow to 39 million people if it follows that formula. And then finally, determine when the population will reach 30 million people. Well, what do you do with that 30? You don't plug it in for the input, you plug it in for the output. So right there. So I'm going to take 30 and set it equal to 21.2 E to the 0.0407 to the T. And so to solve this problem, we'll simply divide out both sides by 21.2. We're trying to get this stuff by itself, basically. And so what do we have then? We get 30 divided by 21.2 equal to, there's going to cancel on the right. And so we just have E to the 0.0407 T. And then we can ln both sides. And we do that because that'll bring that exponent down in front. And so we'll get ln of 30 divided by 21.2 equal to a 0.0407 T ln of E, and then ln of E is just 1, so it's going to drop off. And then we just need to get that T by itself, so we'll divide out both sides by the 0.0407. Let's make that 0 better. And so then T is equal to, so make sure you write down the exact answer. So T is equal to then ln of 30, let's make that 3 much better. So 30 divided by 21.2. And then that's all divided by 0.0407, which is approximately, so now I can approximate, got the exact answer down. And so now I can approximate this thing. And so it's approximately what? ln of 30 divided by 21.2 in parentheses divided by 0.0407. Hit enter, it's going to spit out a number. And so it's about 8.53 years. Let's just round to 2 decimal points for fun. So 8.53 years. So there's a solid answer. Or you can add 2000 since it started in 2000, or you can write in, so we can add 2000 to that if you want. So in 2008 is also a good answer for that problem. Okay, so that completes the review.